for attending this webinar. Today, my colleague and I from application engineering team of MapleSoft will present second part of this machine design webinar called Examples in Machine Design using Multidomain Simulation Tool. So in the next 45 minutes, we will demonstrate how you can bring your CAD design to life using our virtual prototyping and system-level modeling tool called MapleSim, and you will learn how to perform various types of analysis to help you validate your design. So here is the mechanism which we're going to look at today. This is the 4-bar linkage gripper, has equal length fingers or grippers on the both sides. And this linkage or these fingers are driven by two 4-bar mechanisms, as you can see here, and they are moving in parallel in the symmetric manner. So this mechanism is created in SolidWorks, as you can see in this screenshot. And now let's move to the MapleSim, our tool for modeling, and open up this toolbox, CAD toolbox, and see what we have here. So as I already pointed, this is called CAD Toolbox Import Tool, and we recently released that. It allows you to import various types of the CAD models into your multi-domain modeling tool, including the kinematics properties of that. So this toolbox can accept the files from different platforms, for example, Autodesk Inventor, CATIA, NX, Pro-E, SolidWorks, and so on. So in this case, we have a SolidWorks assembly and parts. I'm going to select the full assembly of my system from this folder and click on Open. It shows me the toolbox, and it's going to load the full assembly here. If we look at this assembly from top view, you can see we have two identical sub-assemblies, and since we are only looking at the one side of this gripper today, I'm going to select half of this and hit delete. So it's going to be removed from my part list here on the right side, on the left side. And also, I'm going to separate some of these parts and put them in the groups. So this way, I can have reduce the number of parts which are going to move together. For example, if I zoom in this parts of my assembly, you can see this gripper is already as a one sub-assembly, which I can hide it for now. And then here we have the bracket gripper and a couple of the other parts, which I can select and create the assembly based on them, call it base. So if I hide them, you can see some parts are already gone. So now I'm going to do the same thing for these two links. So one is this one. It's two links and these sockets. I'm going to create another sub-assembly, call it link 2 or link 1, and hide it, make sure everything is gone. And the rest of my system, which is these two grippers and also these 4 sockets, gonna be my link 2. So now to bring it to my MapleSim, all I need is to show them and hit this accept button. So let me put them in the isometric view, and that's it. It's going to load my sub-assemblies as a single component, single rigid bodies with the proper masses and inertias. And now if I open my construct view window, I'm going to put it somewhere in this corner of my screen and lock it to the screen and zoom in. So as I'm going to drag and drop these components into my canvas, 2D canvas, you will see they're going to be placed on the screen. I'm going to zoom in more to give you the better view on this side. And finger gripper. And you can see these are all placed in the right position or location as they were in the assembly, because everything is defined in the single word coordinates in my assembly import tool. And now I bring a link 1 and link 2, and you see all my assembly here. Now to connect two parts together, like these two sub-assemblies, for example, connect these two parts, the base and the link 1. I'm going to open up these sub-assemblies or groups separately by clicking on the subsystems. So in this case, I'm going to click on the base. And since I want to attach it to this link number 1, I'm going to put one coordinate at this point, center of my shaft, which is going to be pointing in the Z direction outward, and call it, rename it to tool link. And then I'm going to add another coordinate to, let me minimize this window, this side of my assembly, which is going to connect my assembly to the fixed frame in my tool. And same thing goes here. I'm going to call it to ground, which defines the position of this part of my assembly into the space, which is my fixed frame. And then I'm going to copy this first coordinate, which I put it on this part, and then click Accept on this window, which now gives me two ports. So if I bring back my construct view window, and let's disable these two parts for now, and see if I hover my mouse over these two coordinates, I will see them shown in the right places which I have assigned them to. Now, if I open up this link number 2, which is this link, and simply select one of this grouper, right-click, and paste my coordinate, that coordinate is going to be pasted exactly on the same spots on this link. And if I want, I can change the name and say this is going to be connected to base, and hit the Accept button again. Now I have that coordinates here, so they're identical. As you see here, one goes to the link and another one to the base. So to connect these two parts, I'm going to enable this part again, back, and flip it horizontally. And I need one revolute joint, which gives me the degree of freedom between these two parts. And if I go to my libraries and multibody library, you can see under joints, I have the revolute joint. And once again, if I hover over this port, it shows me the Z direction is the direction which I want to rotate my parts around it. So I'm going to connect this to here, here to my revolute, and check my revolute joint to make sure it's going to be assigned to rotate around the Z axis, which is by default correct. And then connect it to this link number 2. Now I need one fixed frame also, which comes from the bodies and frames, part of multibody library, and connect this to here. So now you see, as soon as I connect it, it's going to show, like if my assembly is going to jump to the 0, 0, 0 coordinates, which is defined by this fixed frame, and from there, it's going to point in negative Z direction outward. Now, just to make sure the assembly is connected properly in my tool, and it's going to rotate around, we're going to have the movements of the link with respect to the base. I'm going to go to 1D rotational mechanical components and grab one of the motion drivers called position driver, connect it to my revolute joint, and then I'm going to look for the ramp components, which is also part of signal blocks and connect it here. And on my ramp, I'm going to define it to move from the 0 radian to 1 radian after 1 second for 6 seconds. And the whole simulation time is going to be 10 seconds in this case. So just to look at some results or some to probe some outputs, I'm going to add one probe to this connection here and ask for the speed and the angle which is going to be experienced at this joint. Let's play this, and meanwhile I can move to the results. Okay, and let's rearrange these two windows, removing the implicit geometries. So implicit geometries, as you can see here, also are the representations of our multi-body components in the 3D environment. You can turn them on and off. And if I fit these results or probe data to the screen and play it, you can see this is going to move in that direction. So with this simple introduction into the import tool, our import tool, CAD tool, I'm going to pass this presentation to Jonathan. My colleague is going to show you the fully imported version of this assembly and to show you what you can do, what type of analysis you can do with it.
Thank you very much, Upteen. And thanks for getting us started on how the CAD import process works. And so coming up on your screen now is my desktop. And so what we've done at this point is we've continued the work that Upteen had started on, which was bringing in the base and the first link structures, and continued connecting using some of our Revolute joints, the other components that we're wanting to define our system with. And we have, again, our motion driver, that just like what Upteen had put in earlier, where we're going to be measuring our angle theta. And in this case, I've also added in a sensor for the driven speed and the driven torque. So let's go and take a look at what the simulation looks like at this stage. We'll be able to see the actual mechanism moving in the manner that we're wanting to show here. So we can see our probed results in the one grouping here on the left. And of course, we have our 3D visualization like Upteen was showing previously. So now we can see the entire mechanism moving with the desired motion, having a ramped input angle at the base here. We can see that we have torque loading as a result of when the mechanism starts to accelerate, and also again when it starts to decelerate. And we can see the end effector motion. So that's the motion at this point on the gripper, where we can see how it translates in the x direction. If we go back to the MapleSim model, we can see that that's one of the points that we've probed as a point of interest for our model. At this point, if we want to be able to do some further analysis, such as being able to control the endpoint of our gripper system here, and say define a path that we want the endpoint to move along. So for instance, this could be how quickly do we want the grippers to close, how do we want to manipulate an object that's moving in space, or if we want to push an object, we probably can define a path that creates that function very nicely. But to be able to go back to where our input of our gripper is and define that behavior so that they are matching each other can be a little bit tricky. And here's where we can do something like inverse kinematics to go on and help us with that process, where we can relate the desired motion at the output of our gripper system to be able to determine exactly what kind of input we need. To get started with this, I've put together an analysis worksheet that I've attached to this model. And walking through this analysis, we can actually take a look at what the equations are for the system. So here you can see that I've opened up Maple worksheet. This Maple worksheet includes a little bit of a preview window showing how Maple connects back to the MapleSim model. And here, the first few command lines that I'm running here actually link the MapleSim model to Maple, and we have a get multibody function here. This get multibody actually takes a look at what these multibody objects are, so the base, the links, and the end effector with the endpoint on it that we're interested in, as well as it examines the equational constraints that these joints R1 through to R4 put on the system. So as a result, we can see that the system has a 1 degree of freedom, and that would be the input that we're interested in. Continuing down, we can take a look at the equations of motion for the endpoint. So we can use our getFrameMotion command as part of our multibody operation, where we're going to take a look at the finger gripper, and we're looking at the port. In this case, we've called it force, but it's the port right at the end of the gripper, and that's the point that we're interested in seeing. And so we can take a look at what the equations are, and these equations have been written out as a function in terms of R3, R1, R2, to define the motion in the x direction. So that's one part of our equation extraction. The next part of our equation extraction is to get the constraint equations that we're interested in our system. So these constraint equations will be dictated by the construct of our model and how we put those joints in. Here we can see that we have, I believe it's 2 constraint equations, so we can go through and take a look here. So we have our one constraint equation, and we should be able to see that we have 2 constraint equations as well. And when we take a look at what these constraint equations have in their indices, so we have the first constraint equation uses the terms R1 theta, R2 theta, and R3 theta. So does the second constraint equations. So what we can do is rearrange these constraint equations into a form where we can relate R2 and R3 together, so that way we can get them grouped so that we have a form that R1 can be used, and tie it back to how we can remove some of the terms in our endpoint location equations. So we want to combine these two together. Using Maple's solve capabilities, we can solve the constraint equations and get exactly that form. The solve command for these equations can give back multiple different solutions, and I'm going to be using the first set of solutions in this case, but there are going to be more than one, and typically the simpler the solution is, the easier it is to use in your mathematical tool. Just like when you're deriving things by hand, and when you have a simple set of solutions, that's always the nicest way to go forward. So I'll use these solutions that came from combining these two, and I'll use the sub command to sub this, so subbing these results in back into our equation of motion. And now we can see that we have the relationship of the x position only now as a function of R1 theta. This is the equational structure that we want, and so we can take a look at that, and at this point we can calculate what the position would be given any angle of R1 theta. To be able to do the opposite is what we want to do in the end. So let's isolate the equation for R1 instead. And so here we can see that it's a function of an arctan. And what this equation is our inverse kinematics of the system, relating the output position, that is our x position, and being able to determine what angle, R1 theta, is needed to be able to relate those two together. To give you a bit of a sense of that, let's go and plot that x function. And so here, what we've done is we've plotted the position of x, so anywhere in space that is a valid position for our mechanism, because there's going to be a limited number of positions that are actually valid, as well as the nonlinear relationship that comes from this arctan relationship, to go and determine what these angles are. As we can see, these angles are in radian and relate to the rotational angle at the input for our system. So once I have these equations, how do I connect these back to MapleSim and do something useful with it? Well, one of the nice things with MapleSim, we can also create our own custom components. And so I'll just directly copy this equation I'll return to the MapleSim model, and I'll create something called a custom component. This custom component template loads up with a pre-built-in example to help users sort of walk through it and get a good sense of how the template works. But in this case, I'm going to be directly using the equation that I just copied. So I'm going to paste that equation here. The custom component uses the equations in terms of time-based parameters, so R1 theta as a function of time and X as a function of time. And fortunately, I've already had that equational structure form, and I can just proceed on with using the template. So I've determined what my variables are, R1 theta and X of t. Now I can start creating my icon layout that I'm going to be using with this. So I'm going to clear the default layout, and I'm also going to select the default icon display. There are other options available to you, such as being able to reuse any of the component layouts that are as part of the MapleSim library, or you can include your own external image as a nice little feature too. But for now, let's stick with the default icon. I'm going to add a port that relates to the input. So just like we've been determining so far, we're going to be looking at X as the input. So I'm going to say X in. I'm going to assign that to my input port. Let's add another port to the other side. And what I'm interested in at this point is getting the R1 theta out. So I'm going to say this is theta out. Assign that. And now I've got my custom component icon layout configured. And then I'm going to say this is position to angle, and I'm going to call this calc. So this is going to be the name of my custom component. I'll let that generate. And here in my component list here under the definitions tab, I can see that custom component that I just created. I can drag that into my workspace here, and now it's a live component within this. So what can I do to make sure that this is working? Well, I already have a mechanism that's being driven by the input, and I have an output position that has a valid value, but I want to be able to double check that I'm going to be calculating, so using inverse kinematics, using this position as an input, and I want to make sure that this angle that I'm calculating here is in agreement with the angle that I have here. So I'll go to multi-body under sensors. I'll take a look at the absolute translational value, add that to my system, and connect this up. So here I'm measuring the absolute X, Y, and Z position. And so in this case, I'm interested in the X position. So we can use one of our demux components and just grab the X value. So I'm going to grab the X position using demux, selecting only X, and I'm inputting the X position and going to be calculating the theta out. So let's call this theta calc, and that's in radians. If I run my simulation at this point, I should be able to see that there's an agreement between my calculated theta and my input theta in my results manager window. So I have my original theta and my theta calc. They look pretty similar, but let's actually do a direct comparison. So I'll create a new plot window here and directly overlay, and sure enough, they're in absolute agreement with one another, which is fantastic. So that gives me confidence that we've moved in the right direction so far. At this point, I can use this as an input device for my overall system. So instead now of using the driver that we have here, I can say, okay, I would like to use the value that I'm calculating here, and perhaps now I have a definition for what I want the X position to run in. Fortunately, I have an example stored as an Excel file, and here I just opened up the attached Excel file, and you can see here there's the profile, and there's a nonlinear slope where there's sort of smoothed corners on this profile, and then the ramp structure is not identical in the second sort of step motion. So we have nonlinear motion that we would like to use using this Excel file. So if I go into our library set of tools here, we have the ability to use an interpolation table, and I can use a time-based table. Add that to my system, simply select the attached, and I'm going to skip the first row as The first row contains the header information, and I'm only interested in the data table for that. I'll put a probe here so that I can say that this is my endpoint desired, and this is in meters. So now I have data input of the end position that I would like to have. I have inverse kinematics to help me solve what the angle needs to be to drive my mechanism to determine exactly where it needs to make sure that the end position is the desired position and that the model works out properly. So if we run this, we can take a look at the simulation results and hopefully validate that everything is working just well. So we have our comparison we had from before. Now let's take a look at our end position. So we have our measured, and we have our desired. Excellent. We have a good gradients as well with this. Let's take a look at what the animation looks like. And so you can see how the motion has now updated with the response that we're looking for here. So that's fantastic. We now have the ability to drive our system with a commanded input based off of what we would like to drive our system with. And we also have the mechanism that we're driving. But where do we go from here? Well, at this point, our mechanism allows us to say, well, despite what the load is of this device, our position driver will give the required torque to move the system. Right now, it's only moving the system based off of the inertial load that the device is experiencing. So if I take a look at the results, and I say, I'm going to look at what the torque, and I'll present this with torque speed curve. So this is some of the data that's used with it, and I'll also include the torque curve as a function of time. So we can see here that we have two plots now, where we can see the torque of the system and the speed of the system, as well as the torque as a function of time. So we can see that there's a very nonlinear response with this device, but again, the only load that the device is seeing is based off of the inertial load. So I'm going to save these results. I'm going to say no friction. So now I have a reference point. Now, if I want to add friction to the system, there are many different ways of approaching this. There are definitely capabilities where we can add, for instance, viscous damping. If I go into our 1D mechanical system, we can just add a damper. And we can even try and define our own custom component, or we can add other features such as different loads. In this case, what I have actually is a nonlinear damping system that I've just showing here on this worksheet with our friction model. And what this friction model includes is the Strybeck friction, Coulomb friction, and dampening. So here is the equation for our friction model. So we can see that it's a very nonlinear friction model, and we can see the response of their friction system as a function of speed and then what the frictional torque will be. And so we can see that there's a nice sort of notch structure here, and then there's a definite dominant dampening response as our speed increases. We can take a look at some of the key components of this model, which are in each of the parameters. So we have sort of the starting point in the linear region of our friction model. There's a tapered point reaching up to what is known as the static position, and then the viscous or Coulomb position for our friction model. And then you can see along the blue line the dominant dampening response that eventually becomes the main characteristics of our friction system. And this is all defined using these few parameters. So if I want to go and bring this friction model into my MapleSim model, I can again just copy the equations that we have here, and I can go and once again create a custom component and add this to my equation structure. So again, we have the basic structure presented here, and in this case, I'm going to actually do some configuration to make it so that the equation is structured in the way that we're going to be using. So that means making sure that our torque is a function of time, that our speed is also a function of time, so the W term here, and we'll take care of those characteristics. Now, also, we want to be able to relate what our speed is going to be connecting to some of the other physical ports on our model. So we can do that by saying that our speed, so omega, is a function of the differential of theta, and I'm going to call it relative theta as a function of time. And I'm also going to define what theta relative is. So theta relative, I'll put a capital R to be consistent, is going to be the theta, and then I'll say A for the one side, minus theta, and then I'm going to call the other side B as a function of time. So here are my equations. So I have a relationship between the rotational speed, the relative rotational speed, to give me the torque. I have my relationship defining what the speed is, which is the differential of the relative theta, and then the theta is the two measured angles for side A and side B, and the theta is the difference between the two. Simply refresh my worksheet now to extract those parameters that are involved in the equations, as well as the time-varying variables. I'll clear the custom component layout and use the default icon again, and again I'll add 2 ports. This time, I can actually use something in the Revolute section instead of just the signal-based block, which has the advantage of being able to use physical properties of our system. So on this side, I'm going to have flange A, and I'll connect that to theta for the angle, so theta A. And for the torque, I'll call that directly as the torque for the system. On the other side, I'm also going to use the rotational port. I'll use the B definition of it, so I'll change the icon so we can see there's a filled-in icon and a not filled-in icon. The angle for this side I'm going to use as theta B, and the torque on this side I'm going to call as minus T, as it's the opposite side, and we'll have the reaction force. I'll label this my friction and generate the custom component. So here we go. We now have our friction component, and I'll just populate some of the data so that it matches that Maple worksheet just like we had before, and that way that we can get a response that will look fairly reasonable for our system. And their last value here. Okay, so now we have the parameters entered in for the torque and our speed, and this will be able to relate what our system will respond with when we're actually modeling this. Just like in the example we saw before, I can connect the flanges here to either side of our joint. I can allow Maple to sort of relay it out so that it looks a bit nicer, and simulate this. The simulated results now, we have one friction component term, and let's add it to our model. So we expect that our torque load will increase. And sure enough, we can see here a comparison between our non-friction, which is in green for both cases, and now with the added single friction on the one joint driving and adding an additional torque load. However, because we took care of the inverse kinematics, we can see that every one of the models follow the exact same trajectory for both the theta position and the endpoint position. So this is excellent. This means that I can add dynamic loads to my model. I can add friction, I can add forces, and load to the system, and yet still have a device, this position driver, that will take care of the torque demand and give me a sense of what the value is that I need with this additional load. I'm going to skip over to a model here where I've taken that same friction model and I've populated on each one of the joints, as well as I've converted TC and D, the two parameters, into parameters that I put in this here single parameter block. In this way, as I change these values in the parameter block, each one of these here terms will then have their own friction term updated simultaneously. And so we can first run the model to see what this looks like compared to the previous friction configuration, where we only had one friction result. So I'll toggle on the previous overlays. So we have our different results here can be shown, where we can see the one in red is our most recent with all the friction terms, with no friction in yellow, and with only one friction component in green. And we can see also in our time-based data that our friction is now starting to get significantly larger, and as a result, our torque load is increasing. But as before, our endpoint trajectory is perfectly matched. The last thing that is of note that I would like to share today is when you bring this type of analysis that is parameterized back into Maple, you can start creating things like interactive worksheets. Unlike the previous worksheets where I've entered in equations and equations were either given back to me or I created custom components, this worksheet works in a way where I can actually interact with it. So again, we can see that Maple is connected back to MapleSim. I've loaded up the model and compiled it so it can be ran very, very quickly with any sort of parameters that I may be giving to it. And what we can see here at the bottom are my parameters TC and D. And as I adjust any of the values, we can see here on the left that the torque requirements is changing, but our endpoint motion is exactly maintained because we took care of that with our inverse kinematics. And I can explore the different limitations of our model. I can explore what the motor requirements are and get a good sense of what the load capability is. If I want to be able to compare this, say, to motor information that's typically presented in absolute speed terms and absolute torque terms, that's not a problem. I can just simply take a look at the absolute value of those results given. So I can see here that I have 0 at this corner, and I can have my magnitude of torque on the vertical and my magnitude of speed on the horizontal, and still explore the capabilities of this model and see what kind of range I get in my overall system. So with that, I would like to conclude the presentation and thank my colleague Upteen for putting together the groundwork for this model and allowing me to continue with the analysis on it to explore this with you. And what we've been able to do is start with an automated design that was done in CAD, import that model into our MapleSim environment, run an analysis using our inverse kinematics, and using that being able to add additional load. In this case, we're doing nonlinear friction at each one of the joints, and yet still being able to reproduce the exact same motion that we're looking for at the endpoint and get a good sense of what kind of load, in this case being the torque, at our input source.